this meeting, we were always talking about the second one, but we are not talking very much about the first one. Can we make particular pattern? And here's just a very simple example. When with Harold Kwang, we worked on the free electron gas on the STO-ALO interface. And then when you poke on that and you measure the current in the free electrons, you find the domain boundaries which are underneath in the STO. And so if you change the situation in the STO pattern, you change the free electron gas. So that is a typical coupling you can see there. Another one is with Franco Biata in Barcelona. We looked into magnetic coupling, so we take the STO. STOs are ferroelastic material. We put a magnetic layer on there, and then we cool it down, and we see what the domain structure in STO does. We have the magnetic layer on top of it, and what you find in all these data is that the pinning of the magnetic domain walls at the interface between the STO and the magnetic layer is actually non-zero. It's not extremely strong, but it's quite strong. And so we can change the magnetic properties by the underlying STO. Here is a thing which I don't know how many work on reentrant spin glasses, which is a very interesting phenomenon, where you go from high temperature in a paramagnetic state into a ferromagnetic state, so just normal block walls, usual stuff. You go down in temperature and you go into a spin glass. So it's quite interesting that you have these three phases, from the para to the ferro to the spin glass state. And the question is, what does friction do? I mean, Annette talked about friction, and I think it's a very important damping problem. You go from high temperature, here strain amplitude, friction parameter. It's basically amplitude independent, so it's classical friction. Then you go into the magnetic area here where the friction increases with the strain amplitude. And when you go to very low temperature in this regime here, you are in the spin glass state where the domain boundaries can slide over the landscape, the complex landscape of the spin glass. So you have first no domain boundaries, then you have fairly mobile domain boundaries which are slightly pinned by defects and all that sort of thing. So you lose a lot of energy when you move them. But when you go into the spin glass state, you have a sort of very smooth landscape over which they slide, and you have logarithmic divergence here and all that sort of thing. So they have a singularity at TC, the magnetic one. You have the maximum dissipation at this point, and when you go into the spin glass state, it goes down to zero again. So there's no other domain boundaries which can do that. And the idea is really what we call vaulting. I mean, vaulting means basically it's a nice word for wiggling. So if you have a few defects in there, you have a domain wall, you have a defect, then these domain walls locally, it's largely exaggerated here, will bend over, and that costs energy. And this energy is the dissipation which goes into the friction coefficient. I mean, we worked with Ishibashi on that in '96, so that's how it looks like. And of course, when your landscape is very smooth, then you don't have these point effects, and they can just wiggle over them, and you don't see any singularities. So you can do that also in a way by what we call RPS. So we take a crystal, we put some electric contacts on there and a very small voltage. So we are not switching anything what there is. But if this material is now piezoelectric and you switch, you go through a certain frequency range where you're in the resonance condition, they will emit acoustic noise. And this acoustic noise is now wonderful nowadays with new methods. You can go to the next room, you have a long ceramic tube, and there's basically no damping in the tube. So on the other side, you just put a receiver here, and so then the noise goes through here, it's received here, and you can do these frequency-dependent spectra, and you see these resonances. So you can see in calcium titanate, the polarity and the piezoelectricity is only in the domain walls. There's absolutely nothing in the bulk. And you can see these few domain walls alone, when you put an electric field in, they start to wiggle. And that's enough to produce a loud, reasonably loud, acoustic noise. And so if your microphone is good enough, and you can buy these things. I mean, we're not building them. You buy them, and they're quite commercial, good machines. You amplify it for a while, and then you find these resonance curves, even though the functionality is only in the domain wall. So the times where we could speculate there's a lot of stuff happening in the domain wall, but we can't see it, sorry for that, are over. I mean, we can see in electron microscopy, we have seen lots of talks, beautiful talks, where we can see the shift of the atoms in the domain wall. Now we can see the piezoelectricity directly and so forth. Now here is the ferroelastic part, so I squeeze a crystal, I get my primary domain walls or domains, the secondary domains, vertical, then the tertiary ones, and so forth. And if I carry on with that, I go almost to a glass state. And if I rotate the crystal by a little bit, then you can see it's the same crystal as lanthanum aluminium oxide. You can see that this behavior now is very angular dependent, so I can actually, in an engineering fashion, make patterns which are characteristic for what I need to do. So if I want lots of them parallel like that, then the second one is good. The first one is not, because they had 90 degrees boundaries, lots of them in there. And so we can do that quite well. We have nucleation center near the surface. And of course, this process can be stopped. Now, what you can see is that these domain boundaries shoot in. They're actually quite fast. And we believed for a long time that the fastest domain boundaries are actually the needle domains. The needle domain can shoot in, and you can retract it relatively fast. But that is not quite the case. There's something where we can see here the domain boundary going to a surface. This is a surface. This one is now looking sideways on this needle domain, right? And you can see here it's pinned at the surface. Now we pull it back. It's quite interesting. You pull it back, and what it does is unpeel from the surface. So the right-hand side here peels off. Now the interface is here, and it peels more off, and that is a relatively slow process. But when the last thing here comes off, if the last bit where it pins comes off, it's incredibly fast. We're really talking about, as fast as we can have resolution in these high-speed cameras. I mean, they're incredibly fast. So first it peels off a little bit, and then suddenly the last bit makes boom. And you get this reduction here, and then, of course, it proceeds via the defect damping relatively slowly. The fastest one actually found, I mean, it's very similar to that, we found by computer simulation, by MD simulation. And so we looked into all sorts of domain boundaries, put external fields in, and saw how fast they could move. And the fastest we always found are these kinks. So you have a wall, you have a kink, and there's a wall again. And then here, of course, you have Eshelby and all that strain fields. Now, if you put the field in such a way that this thing moves to the left, it goes to the left, and when it hits the surface, it emits an acoustic signal. Right? Because you change these atoms. So now you can measure the speed of that stuff by how often it hits the signal. I mean, you know where it starts in the middle, or somewhere in the middle statistically, it hits the surface, and then you know when it arrives. Now, I should say, this is a methodology which we have developed now for lots of other things. I mean, it's not just for ferroelectrics. We do it in particular for the collapse of porous material. You take porous materials, you compress it, then you have the same signal, the acoustic signal coming out. And these signals look like this. So you have here time or temperature or whatever. And you find all these signals which come out are incredibly sharp. Incredibly sharp. It's the sharpest we can do by the electronic means we have. I mean, we are now limited by the amplifiers and whatever we have to measure them. And we cannot go into picoseconds, but we can do nanoseconds. So here is a typical example for switching in barium titanate. We have seen that many times. So if you take a barium titanate, you put a single crystal, you put a field on there, then you have these kinks and whatever, the fast things moving in there, and each time it hits the surface, it gives you a signal, right? So now we have a handle for speed, and the beautiful thing is, those who are a bit more interested in theory, there's a huge body of theoretical physics, statistical mechanics on how these processes work. And one you learn immediately is it's scale invariant. So it means if you measure the probability of a jerk, we call these jerks, as a function of its energy, it should be a power law. So log should be linear, which means you can have the same process on a large scale, a small scale, a fast scale, a slow scale, and so forth. And then there are tricks how to check whether you're really scale invariant and things like that. So it's a totally universal behavior. And in particular, the Barcelona people are very good. And you look at the energy which is transmitted as a function of the amplitude what you put in. And you know energy is always amplitude square, roughly speaking. Now, in these fast processes, that's not exactly true. It's amplitude square minus epsilon, because the profiles are different. And so you determine these exponents, and they're typically in the order of 1.9. So it's a little bit below the square dependence. So here's a typical example. You have a porous material, you do exactly the same experiment, you squeeze it. Each time something collapses, something fast happens, you get a jerk. Then you look at the probability of finding these jerks, and you can see here over 6 or 7 orders of magnitude, it follows the power law and the scale invariance perfectly, right? And now, just to demonstrate, also the time intervals between jerks is totally determined, so there are critical exponents for that. But the order of magnitude of the length scale is, you know, if you look at the blue and red and so forth points here, they're from nanocrystals, so what I just showed you. The green ones are from Californian earthquakes. So whether I take a nanocrystal or Californian earthquake, collapsing, what is happening? The friction is happening. The friction determines that. Each time a friction event happens, energy is transmitted, and so forth and so forth. And they then happen in avalanches, avalanche theory, which you can all unify. So you have a unified version of what these extremely fast movements can do. So here I want to show you how that happens in a computer simulation. Now going back to the king, which is our best example. So we stabilize this one, we destabilize this one, and we do it by this what we call zipping. It's like needlework, right? I mean, there's a king going forwards and backwards and forwards and backwards and weaving the new phase in. Now what is interesting is, of course it happens in a statistical way, is this phonon branch which comes out. I mean, when they go, of course they lose some energy. It's not very much, but they lose a little bit of energy, and the energy goes backwards. I mean, the phonon branch goes backwards. And of course, if you remember Mach cones, that's a Mach cone. So these guys, just from inspecting optically, you can see they're already supersonic. So they're going so fast that the forward beam in the phonon is folded backwards, and you can see it in the backwards direction. So now you can measure or determine the exact form. So here again is the king. This one is the Eshelby strain matrix. So that's this. It's a cross basically. And then when you look into so here is the front. The king is in the middle there, and when you look at it, oh sorry, it's moving forwards, and you can see this branch when it gets faster is folding backwards, and these ones are enhanced, and that's exactly the same as if you shoot a bullet and you look into the Mach cone which goes backwards, right? So these kings, so here's the actual king, there's a topological king at that point, is moving forwards with a speed which is faster than the speed of sound. In this case, of course, there are many speeds of sound because you have different elastic constants in there, and so that's how it works. So here is, over time, these are the speeds 4.38 kilometers per second is one speed of sound. There's another speed of sound. And the top one here, 9.58, is the fastest speed of sound in that particular material, I mean, as we simulate that. And here is the speed as it is seen by the king. Now, what we tested here is how far is that actually ballistic? I mean, it's not totally ballistic because the phonons are going out. But how much of the energy is it? Now, it turns out it's a very small proportion of it. So if we accelerate the king and we switch it off at this point, then you can see it continues. The king continues with the same speed. So it's a ballistic effect, or nearly ballistic effect. And then we did it a little bit later and so forth. So if we keep on accelerating, we have the, when it breaks through the first sound barrier here, then we have, of course, the Landau-Ginzburg renormalization of the mass, of the Düring mass. So it should not go through it, but it does. It breaks through here. Here's the next speed of sound, again, the Landau-Ginzburg argument. And here is the end of the crystal. I mean, we can't go further, because when we accelerate these guys, at some point they will end up at the other surface of the crystal, even in the simulation. I mean, we can't go on forever. So then it has to go back to zero. So you can see here it goes up like this here. So there are various mechanisms. Here you can see again the phonons which come out. And it's a very interesting mother-daughter mechanism, how the metallurgists call that. So if you have a king which moves near or above the speed of sound, at some point, if there's a defect or something, they're too fast to be stopped by the defects. They just go through the defects. But if there's a defect, they do a daughter effect. So here is the thing coming. At that point here, so you go here, here, then there's a defect, and it produces two new kings. So the original king goes through. At the defect, it nucleates two more kings, and of course they have to maintain momentum. They would go in opposite directions. So the mother goes on with the same speed. It's not slowed down by giving birth to the two daughters, but the two daughters then go into the opposite direction. And that is something metallurgists knew already for quite a while. When they asked the question, you break some metal, how is actually the breaking happening? And we know it's happening at the interfaces and so forth in martensites. So how does it work? There are suddenly many more kings than originally were there. And it seems to be that the kings, when they move fast enough, they hit a defect, they make two more kings. And then they make two more kings and so forth. And then the entire interface here becomes brittle. And that is the Eshelby solution for that, so how the deformation waves go through it. So here again, now shown again as the position and the speed. So this one is the position of the thing, the first derivative is speed. So this one is the speed. It breaks through the first speed barrier. It breaks through the second speed barrier here. Then the third speed barrier going through that one, and here it's above even the fastest speed of sound in that particular material. So we are really ultrasonically fast kings going into the domain boundaries. Now that is quite important, because what you see is, I mean, we have discussed so far the functionalities by electrons. I mean, these domain boundaries can be metallic; they can go through there, or you can have ionic transport. I mean, ions love to be on domain boundaries. They hate to be in the bulk. So we can transport that, or we can have dipoles. We can have dipoles going through. But all these are relatively slow process beside the electrons, of course. Now here what we are seeing is that the kings themselves are extremely fast. So it's another possibility, for instance, to build a memory device where you go from the king up, down. I mean, you have an electric signal, it goes to the next one, and then it's down, up, and it goes forwards and backwards at enormous speed. And that's exactly what Stuart Parking is doing for the magnetic material in his stuff. Now, I want to end up with a by chance discoverer which was slightly stimulated by results from Berkeley, but also from others. So here is, by the flexoelectric coupling, we have the dipole moment. So a twin boundary has basically always dipoles in there. So here's one twin boundary, and the apex on that side, the twin boundaries are looking to the left. Here's the next twin boundary, where the apex is on that side, and they're looking to the right. Now, you have to connect this one with that one, and you do it by this vortex. So here you have the same, you have a vortex here, you have a vortex there, you have a vortex there, and you have a vortex there. So these twin boundaries are in fact always, if they're close enough to each other, always connected by vortices. And these vortices themselves are, of course, an excitation. So you can see here, we don't put any forces on, we just let temperature do its work. And you can see the vortices are actually slightly fluctuating. So they're not stable. It's not like the twin boundary. The twin boundary is totally stable. It wouldn't move a bit by temperature. But the vortices here are really on such a low energy scale that even temperature can move them around. And so if you change the geometry, again, here's a twin boundary, here's a twin boundary, you have these vortices in between. And if you make the spacers between the twin boundaries bigger, then you can have two vortices and stuff like that. So you can actually play with the vortices in the same way as you can play with the twin boundary. So let me stop by saying, so what is the excitation? I made a spiel about the fact that the vortices are very mobile. They're really, even temperature can change a vortex, unless they're chemically pinned, but they're not in this case. And so here, if you do the same for the jerks, I mean, how many steps do they do? You look at the probability of making a step and so forth. You plot and you look whether it's scale invariant. So in the crystal, all the stuff which is happening at low temperature here is scale invariant. But if you look at the vortices, you can see it's not scale invariant, slightly bent, and at higher temperature it's massively bent. And that means the temperature effects are seen primarily at this point in the vortex lattice, and they're not seen in the domain lattice. So again, you have a separation here of energies. I mean, the energy of the vortex is very low, and the energy of the domain boundaries are very high. So I stop with that. Thank you very much.
Thanks a lot. So please have time for questions. Yeah.
Eckhart, for just other reasons which you know about, I would like to know, if you take tungsten bronzes and you have the domain walls, you make them superconducting.
Yes.
Yeah, but what is the origin of the superconductivity in the walls?
Well, we don't know for certain what's in the wall, but if we make the entire material superconducting, which we can also do, I mean,
This
even
is
the
what
matrix.
I know.
And then it's quite clear it's real space pairing. It's not BCS, and it's bipolaronic prefabricated bosons, which then condensate. So it's a Bose condensation.
Yeah, but if you go to the walls only.
Well, we assume it's a similar thing, because the walls are about 2 to 3 nanometers thick. So they're not just one atomic layer, it's 5 atomic layers.
It's still very tiny.
It's very tiny. It's very tiny.
So
There's a big discussion on that, and the Russians argued that in truly two-dimensional you can't have it, but if you look at Kosterlitaulis, you know you can. So I don't know, but the best bet right now is real space pairing. There's no evidence for BCS.
Yeah, but you cannot tune that by, for instance, changing the length scales of the domain walls by...
No, we can't do that. I mean, the thickness of the domain wall is fixed.
Did you ever try to manipulate the walls?
Yeah, that would be interesting. We can, I mean, so far the superconducting properties are completely independent of how we make the walls. We can dope them with sodium, lithium, potassium, or we can just take oxygen out. And the currents and JC and all this stuff is exactly the same for all of them.
And wouldn't you expect that you have something like Josephson junctions between the
Yes,
different
yes,
walls?
yes, absolutely. That's what we expect. So if you have a needle which touches something, it's automatically a Josephson junction.
Yeah,
Then you could have an enhancement of the superconducting.
Yes,
current.
absolutely,
Yeah.
absolutely. That's the
Thank
idea. Yes.
Thanks a lot. Yeah.
Eckhard, thank you for this encouraging the field as usual. I wonder, is there supersonic motion of these kinks expected in perovskites like lead titanate or barium titanate?
Yes, absolutely it is. And I had long telephone conversations with the Berkeley guys, you know, Ramesh. And the problem right now is very odd. Everybody sees something. I mean, all what you need to do is to do a dielectric experiment. You measure dielectric, right? You put a field on and you ask when is something happening, right? On time. The problem is we have no electronic means to do that in the gigacycle. I mean, the time scale here is a picosecond. So we are talking about a few picoseconds for a finite sample. In a picosecond, it's all over. But either we can make enormously big crystals to go to 5 picoseconds, or we have to improve our electronic means. We have to have faster detectors. We have to have better electronics. But it's not impossible. I mean, perhaps we have to work with the klystron, or I don't know what we have to do. But certainly Berkeley is working pretty hard on it. So, but I think what you said is exactly right.
Eckhard, I just want to understand the simulations that you showed, I suppose, were probably two-dimensional. Is that right?
We have
And
done
so-
2 and 3, both.
Okay,
both.
so are there qualitatively different
No,
features in
no,
3D?
No. What we have tried to do at the question of Jim, who just fell asleep there, is we want to know whether the vortices are pitched or not. And in 3 dimension, we don't see a pitch. They are just columns. Yeah.
Okay, thanks. So I think we should move on. Let's thank the speaker again. The next talk will be given by Alexander Reutburt. The title is High Stress Polydomain Structures in Epitaxial Films.
Thank you. I feel myself a bit uneasy because after excellent experimental work which was presented here, excellent dynamic work which just now, I will be talk about very primitive things, pure thermodynamics, a very simple thermodynamics. But I think some result unexpected for me may be of interest for you. So we started with something which happened about 40 years ago. 40 years ago, I don't know why, I decided to look about phase transformation in epitaxial film. We come to conclusions it should be form such kind domain structure. Why not goes? Like this. No, by the way, sorry for this not very good picture. It's old, very old picture, ancient pictures, because it's about 40 years ago. But at least you can see there is two kind domain structure, primitive one for 2 domains, is then completely relaxed if you have 3 domains through the alternation of the domains, second order domains. Okay, that happens 1973. No, 1976, okay. 12 years, nobody paid attention for this work. What happened, maybe never mentioned at all, if the suddenly great interest to high temperature superconductors, about 80s, 179, about 181, is this, no, about 188. There is great interest in new superconductors. If people observe films, yttrium barium copper oxide, fast high temperature superconductors, observe in films, observe such kind of domain structure. After that, great interest about this. I have some paper too, about 10 maybe more papers about such kind of domain structure in superconductors. And suddenly, somebody is also remember about this, it suddenly becomes hero of this story. It's so exciting that after that, all my life in the United States, about 25 years, I studied domain structure in such kind of films. And what finally, I think almost come to conclusion about this activity. We wrote such a review paper with collected more than 100 papers, experimental, theoretical. Yeah, I think we completely exhausted this problem. By the way, first of all, my great gratitude for the people who was reviewer of this great paper. Thank you very much. I hope somebody here. And so finally, I decided that for me, problem is finished. Okay, but when you come to the conclusion, I suddenly recognize there is something missed. All this story constructed all the story is constructed in suggestion. The elastic property, all the phases which consider the same. And by the way, that's usually done even if the people use phase field modeling, which is very effective in this case. Usually they use the same approximation, the same elastic property. And now question is, what is properties different? Is this result? We do this very modestly, write about this question is the conclusion of this paper, that we not consider this because there is no enough experimental data. No, after that, do something which make me to consider this problem more seriously. So today I'll tell you about this new discovery. But before that, I'd like to remind you, what does it mean, how we can get this elastic domain? You see, problem consists from two parts. No, by the way, that is exactly geometry of the high temperature superconductor, the tetragonal phase transform into orthorhombics. What on the left side you can see this A&B call it. What does it mean, what necessary conditions for formation of such kind of domain? But let's just look at the right side. View. By the way, where is it? Thank you very much. Look at this part. We consider as U initial phase, high temperature, which completely fitted to the substrate. Separated, it transformed a new domain, white and black. Clear that in white case will be shorter, in black will be longer. Then you can combine together such a way they have the same size like your substrate. After that, your film has the same completely compatible with substrate. In principle, you have the same sizes, but if you put on substrate, clear they immediately can interaction with substrate, and again you have stresses. To avoid this, we have some process of homogenization. Let us cut this film, which completely correspond to size of substrate. For the very thin layers put together, after that you have all the stresses will be concentrated in a small area near this interface. That is usually what homogenization help us to put the film which we have the same size like substrate, pull without long-range stresses. Okay, that is, so what I would like to say? The creation of such kind fitting of the separate film to substrate, it's necessary conditions for formation of the domain. If you cannot do this, you cannot, your domain and structure not be equilibrium. No, of course, if you have, instead of the two product phases, have something high temperature phase, of course, you should keep in mind that high temperature phase has different free energy, so of course it's not so simple, but idea is the same. You should do something which satisfy condition of condition of the compatibility with substrate, and then subdivided in some small part, you have final result. Okay, now, what you have in this case, what was exactly what happened. In the case of high temperature superconductors, you have such kind of the domain, all elastic energy concentrated in small area near the surface interface. Area, the thickness of this area about thickness of period of the domain structure. Period is proportional square root of the thickness of this. You can easy to show that very often normal thickness of the film about not less than 100 nanometers. All time you can neglect completely this energy. All energy is determined only by energy of the bulk film. Okay, by the way, I show you one of the first observation depend of the thickness, dependence of period of thickness of the film. You see very good relation to square root relation. Okay. Now that is something which you can know. And now question is, what happened? What I show will be very important, the property, elastic property of the film, initial film. Both product, the same, you have the same elastic property. Now I show you what happens if the property will be different. Okay, for this case, I like to consider with you what you have in this case. These three different what does it mean? Let's show you, let's consider this film which you prepare before transforming domain, or if you like, even we consider rod, because we consider one-dimensional stress in the film. There are three different cases. First, property is the same. In this case, you have diagram which you can see here. Okay. You have three phases separated by straight line, because that is clear because you have the same. All the models the same, because you have uniform film. If the film is not uniform, you can see very, very nice parabolas. In case if the both elastic property, white and black phase, the same as the symmetrical parabolas, which you can see here. All the space, stress, temperature, subdivided temperature. Instead of temperature, use delta free energy, which proportional, more or less proportional temperature. Of course, so simplify this picture. We have symmetrical parabola like this. But if the modulus different, what do I have in this case? The initial phase, gray phase, have more soft phase, so her modulus is minimum. Then we have more next phase, softer phase on the right side, which corresponds black. More strong phase is white phase. You have diagram which is presented here. So you can see that one parabola becomes higher curvature, another smaller curvature. It is a very strange story. We have some intersection here. With, first of all, we have a point here, which is point of equilibrium. And then we have some another point here, when the continuous of this parabola, which is boundary between the gray and black, intersect here. So we have this, you can express this black face. If you look at this, it's very strange and unclear. By the way, if you remember diagram of composition diagram, it's look if you can see some reminds here, point E reminds something eutectic point. This point reminds something teratectic point. So we have transition from black to if you to negative stress mode. We have transition from white phase to black phase, a gray phase. Opposite we have here. That's something which corresponds if you have such kind of experiment, do such rod, or this initial film which I like to put on substrate, extended by stress. No, but reality not extended. We have control parameter, not stress, control parameter is strain. What do you have in case of strain? What should this mean? No time more. Oh, sorry. In this case, solution goes through the solution of the problem. We should look Legendre transformation, and then you can find something which called, if you now call method of the common tangent. So we understand there is some common tangent between two black and gray phases. So we have some mixture. So the diagram looks now like this. What you can expect in case the property is the same. You have something which looks very, very similar like eutectic diagram. So we have middle, we have phase, initial phase, that you have some black phase and white phase, intermediate cases, which can give you formation of the formation between lower temperature of the equilibrium or mixture of the initial phase or one of the final phases. What happens if you consider case that is case, I remind you again, what happens if you have a different property of phase, but again, great phase, initial phase, have more soft phase, minimum modules, and black phase next, white phase have the same modules like black. You have symmetrical pictures look like this. You can see area of the single phase, area of mixture of the phases, have your domain structure observed here. The last thing which I like to show you. By the way, one moment, I like to put. Now I like to consider case when the property of the final phase different. One softer, another phase. One softer, another phase more rigid. Strange story is that in this case you have it's happened if you have anisotropic property of the final phase. The diagram now looks such a way. That is final result if you want. Diagram in this case looks, no, again, that is stress dependent, that is strain dependent. That's exactly like we have one point which corresponds here, E, which corresponds eutectic transition, and one point which corresponds to eutectic composition. That is what happened high temperature. But what does it mean this? What happens low temperature? So we can see low temperature. If you come to low temperature, lower than this graph, Okay. Sorry. I can't. Oh, sorry. Why not go back? Sorry. Finish it. One moment.
One more.
No, one more.
Sorry,
More. Oh, this is okay. Look what's happened finally. If you look what happened at low temperature phase, you can see for low temperature phase, because we have some anisotropy of the product, you have two lines which correspond to this. So we have really two intersections. First you have equilibrium here. Common area here, so some area. What is it? Area corresponds to the main state here. What's conclusion? What's really point of this? If you have different properties of the phase, you can expect that exists not only polytwin area here, but there is some polytwin area in stressed, very stressed condition. So what does it mean very stressed? It's possible to estimate. We have this estimation that about sorry. How we go back? Give me last picture. Previous I finish. No, more. Back. Yeah, back, please. Back. Oh, okay. That is solution of this problem. That is I show you stress. Area of stress, whereas we can expect absolutely not predictable before some new area of the existence of a polydomain state. This stress about if you this elastic modulus, is elastic modulus different by 50%, we can expect something like to epsilon 0 multiply 0.5 to multiply 0.5 modulus. So it's not so huge stress. So realistically, it's possible to expect, it's a good film, and we can stress him so much that we have, first, we have possible to have polydomain area of some no stress at all, and then is some stress area. I think that this may be a very interesting story because property, this stressed state, may be absolutely different. It may be some interesting we have get this. So, come to conclusion, I tell you maybe I think I do what I wanted. I'm not sure that this is perfect. So first of all, we consider with you necessary condition of formation of the domain, because when you consider the place, I don't cut it. I don't know what happened if I cut it, what happened when I put on the substrate, because it's possible that there is domain because after cutting, all the area of the plate is compatible. Maybe it's not compatible, but it means that necessary condition, what we consider here. Then possible so some cases we have domain, all the story is correct, and some not. But at least we can look in something in this area. Second, more important result is to show that elastic anisotropy of product phase resulted formation of stressed and unstressed polytwin. Unstressed polytwin is something which we know about maybe 30 years. About stress, it is something new. and expect maybe there's something interesting. Now I tell you that we consider only necessary condition for formation of such kind of the polydomain structure. But all this story can be applied if you like to consider the rod. If you have nanorod, all this diagram which I show you will absolutely correct. So all this picture which I give you information. What will be fracture, phase fracture of the rod if you have fixed its size, step by step change this length. After that, all this diagram you have absolutely describe this phenomenon. Well, that's all. Thank you for your attention.
Thanks a lot. So questions? No questions? I guess we're waiting for coffee probably. So to conclude here, let's thank again the speakers and all others.